A machine fills bags with flour. The weight of flour delivered by the machine into bag X grams is normally distributed with a mean of mu grams and a standard deviation of 30 grams. To check if there is any change to the mean weight of flour delivered by the machine into each bag, Olaf takes a random sample of 10 bags. The weight of flour, X grams, in each bag is recorded, and the mean was 1020 grams. We want to test at the 5% level of significance the following hypothesis. H0 is that mu is 1000, and the alternative is just that mu is not 1000. So that is going to give us a two-tailed test. So if we consider this normal distribution here, and we have a two-tailed test totaling up to 5%, by symmetry we're going to have 2.5% at this end and 2.5% at this end. And remember, that is a probability of 0.025. Just divide the 2.5 by 100. So let's think about our distribution. So it's going to be normally distributed, and with H0 being that mu is 1000, that means that we will take the mean as 1000. You always work with the model you're proposing. This is going to be 30 squared, but remember, for the mean, we're going to divide by n. And so this ends up being a normal 1090. Now, using the calculator, we can work out the probability that x bar is more than 1020. And that gives us 0.0175. That means it's somewhere here. Remember, this is 2.5% or 0.025. So this number is smaller. It must be further down the tail. And that means it's in the critical region. So that is in the critical region. And that means there is evidence to suggest, so evidence that the mean weight is not 1000 grams. Olaf decides to alter the test so that the hypotheses are that H0 is that mu is 1000 and H1 is mu is greater than 1000. So this is a one-tailed test. He keeps the level of significance at 5%, but now it will all be at one end. He takes a second sample of size n and finds the critical region, x bar is greater than c. Find an equation for c in terms of n. So this time our x bar is a normal 1030 squared divided by n. We don't know what that number is this time. And we know that we're taking a one-tailed test. So in other words, it's going to be down here, such that this is 5%. Now, our standard normal value for that, which we can look up from the percentage points table, is 1.6449. We can calculate that on our calculators in all likelihood as well. And that means that what we need to do is standardize the information here. This value, of course, is the C, because it said the critical region is x is more than c, so c would be the boundary of that region. Okay, so there's the mean and there's the variance. That means the standard deviation would be 30 over root n. And so to standardize, we do C take away the mean divided by the standard deviation, and that must be equal to this value. If this C is on this distribution here, and we standardize it, we'll get the value from the standard normal. So we can rearrange that to C is equal to 1000 plus 1.6449 times 30 divided by root n. And calculating, that gives me 1000 plus 49.347 over root n. And I'm going to need that later, so I'm going to call that equation 1. When the true value of mu is 1020 grams, the probability of making a type 2 error is 0.0050 or 0.5% to two significant figures. Calculate the value of n and the value of c. So they're giving us some more information. So the first thing to remember is what a type 2 error is. And that is accept H0 when H0 is false. Now we're still working on the idea that mu is 1000. So if we think about two normals like this, this one here has its mean at 1000, and that's what we're using. And this one here has its mean as 1020. And the value of C is in here somewhere. We're going to be after our actual value being here, so that it gets accepted. So we accept the H0 is 1000, even though this is 120. So this is our value of C just here. Now in the question we were told the probability of making this type 2 error is 0.5% or 0.0050, and we can look up the Z, the standardized value for that, in our tables or using our calculator, and it's negative 2.5758. I know this is symmetrical and there's a value out here, but we know that we're looking at it being less if we're going to be accepting this 1000. So it's at this end compared to 1020. So the value is going to be a negative value when we standardize out here. Remember, when we standardize, this would be 0. So what we need to do is standardize based on the 1020 now. So what we're going to do is we're going to have C take away 1020 over 30 over root n. We've got the same standard deviation. This time that's going to be negative 2.5758. So let's call that equation 2. And remember, we're trying to find n and c, and now we have our two simultaneous equations. So what I can do is replace the c here with the stuff from equation 1. So let's put all of that in, and we get 1000 plus 49.347 over root n, take away 1020 all over 30 over root n is equal to negative 2.5758. And all we have to do now is some algebra. It's not absolutely straightforward, but let's work our way through it. So, first thing I'm going to do is take this up over here. And then when I've done that, I'm going to simplify these terms here. So that's going to give me 49.347 over root n is equal, take away 20 is equal to negative 77.274, which is just 30 times negative 2.5758 divided by root n. And then if we bring this over here and add and bring that over there, we get 126.62 over root n is equal to 20. So root n would be equal to 126.62 divided by 20. Root n is equal to 6.331. And n is then 40.08. But remember that n must be a whole number, so the 0.08 must come from all the rounding that I've done. And so we're going to say that n is equal to 40. And so it must be an integer. And once we've got that, we can substitute back, and c is going to be 1000 plus 49.347 divided by the square root of 40, and that gives us 1007.79. And in the mark scheme, anything which rounds to 1010 was accepted.